I'll be using Lake George as an analog for the future. So we can use the Lake George sediments to go back in time to say, okay, if we raise CO2 up to 400 ppm and we're now at 420, but the last time it was up that long ago was 3-4 million years ago. And to get analogs for that, we have to go that far back in time. And that's the kind of game I play. I have spent 2 years of my life on research vessels going around in ships, collecting deep sea cores. So we can play these games going back in time tens of millions of years. And so I had a bunch of really, really terrific colleagues that made me do a terrestrial project, which was the Lake George project. And we're still working on that. It's been the gift that just keeps on giving because the guys at Canberra Sand and Gravel have continually let us sample and watch as that quarry has been worked on over the past 10 years. And of course, it's changing all the time. We get to see new things. And I won't be talking about that today, but that's another terrific story. What I am going to tell you about today, and I'll do the professorial thing, I'll tell you what I'm going to tell you, is we had a former student by the name of Kim Patrick, who came to ANU 12 years ago. And he'd been working on groundwater studies in Southeast Asia and in Europe. And he said, you know, you might have a hidden big reservoir of water in the highlands of New South Wales and the ACT. And so Bear McPhail, who was our hydrogeologist at the time, said, okay, we'll put a PhD student on that. So we did, and her name is Sharon Gray, and she's just finishing up now. And so when Trixie contacted me about this talk, I said, well, can I talk about Lake George again? And she goes, no, I want you to concentrate more on the upper Murrumbidgee catchment, which we can do because we've just pulled together a phenomenal amount of data on the upper Murrumbidgee, rainfall, overland fall, and the geochemistry thereof, or chemistry of those waters, and of course the volumes. And we had, part of Sharon's project, we put out 20-some rainfall samplers, which we collected over a number of years. And because she did it part-time and took maternity leave, her PhD extended out over a decade or so. And so that's a real luxury because we end up with a long-term record. And the other luxury about the study that we did is that it included that climactic drought in 2019, which answered the original question unequivocally. And so that's what I'm going to talk about today. All right, so we've seen this picture a couple times today. The Thalwa Bridge, no flow in 2019, and then happily flowing again later in 2020. 2019, from a groundwater perspective, and for the first part of this talk, I'm going to talk about groundwater, was extraordinary. And obviously the superficial manifestation of that was water flows all over New South Wales. It wasn't just the upper Murrumbidgee. Basically, every major river in Australia stopped flowing. So these are the questions I want to answer or talk about. And so I'm going to start with this record from Lake George, which it really is our best rainfall record in detail for this part of the world. It just is. Because Lake George is an enclosed catchment. What flows in and doesn't evaporate accumulates there. So we see that when whitefellas showed up in 1820, the lake was high. We went through a dry period to about 1860. Then we went through about 50 years of relative wet times. And then 50 years of relatively dry times. And then from 1950 through roughly to the end of the millennium, it was so-so, it was okay. but not huge. And then we had the millennium drought, which in many ways was only just punctuated by rain in 2010 and another rain event in 2016. And then obviously it was bone dry for 2017, 2018, 2019. And they're now calling that the tinderbox drought, right? But in many ways, it really was an extension of that millennium drought because the whole groundwater system did not recover. And so when you're talking about overland flows, in times of dry periods like we've had for, like, say, the last 6 weeks or so, and it stops raining, it's your groundwater input which keeps your rivers flowing, if it's not coming from snowy hydro. So we have had these drought periods which are significant. And I don't know if you saw Tim the Yowies Man article in the Canberra Times, but one of the guys that helped us with the Harry Osborne with the Lake George project, he actually helped fund it. His great-grandfather or great-great-grandfather had to abandon the original Corrandooley homestead by rowboat because they had one of these big rainstorms. The lake came up several meters very rapidly, and they literally abandoned it by a rowboat and couldn't go back and dismantled it and rebuilt it up on the hill. So these things happen and have happened. So yes, indeed, Australia, particularly this part of the world, land of red dust plains and flooding rains. The thing that I've been trying to get across to people in public lectures I've been giving recently is I had a professor back in New York, a guy by the name of Jim Hansen, not the Muppets guy, but the guy who was the first person to testify to Congress about climate change in the 1980s. And he was the one that put together one of the first climate models at Goddard Institute of Space Science. And he's been writing about climate change now for the last 40 years and just sort of banging the drum. And one of the things that he talked about when he was first talking about trying to get people to understand how much energy is getting put into the system. This is the atmospheric system by the greenhouse effect. And he started out talking about incandescent lights every meter over the entire planet. And he found that didn't resonate with people. They couldn't relate to that. So now what Jim is talking about is, okay, it's 400,000 Hiroshima bombs a day. Okay? And that gets people's attention. And that's probably a conservative estimate for how much energy is being added to the system. And the reason I'm telling you this in this context is, you see every one of those bumps on the graph? If you scroll backwards in time and add all that energy into the system, each one of those high points would probably be double, at least. Okay, so hang on to that. That's important. Because every liter of atmosphere out there is holding more water vapor than it used to, by the pure virtue of the fact that it's warmer. And the capacity for air to hold more water vapor is not linear, it's exponential. And this is what a lot of climate scientists, including myself, are really, really concerned about. Because it means all our events are going to be magnified. And bringing water in from the ocean, which is warming up dramatically as well, it's just going to be carrying a lot more moisture. So we need to adapt to having rainfall events that deliver a lot of water. And another thing that I've been telling the forums I've been talking to is, back when I was a kid, say in the 1970s, a big rainfall event was 2-3 inches of rain. That's a big deal. Now we're talking about rainfall events where you're getting 20-30 centimeters of rain in a day. That simply was unheard of 50 years ago. And that is one of those true symptoms of climate change as we know it, that we've seen unfold in my lifetime. So this is a big deal. Okay, so during the millennium drought, streams flowed all the way up to 2009. At the end of the tinderbox drought in 2019, stream flow stopped. I'm not talking about rivers here, but I'm talking about streams, and that they were gone. Because when we started sampling in 2017 for Sharon's thesis, there still was stream flow. But by the time 2019 rolled around, not only were the rivers done, but we couldn't sample anything. So it was pretty clear. Groundwater recharge is typically, in most areas, about 10 to 20% of rainfall gets into the surface groundwater hydrology, unless you're in Lake George and there's a clay pan, and then maybe it's 1 or 2%, but that's another talk. We are going to get changes in precipitation regimes, and we're seeing that happen. And again, one of the things you learn as a paleoclimatologist, we have this luxury of seeing time telescope. So I deal with data sets that are looking at changes over thousands of years, which extend out to millions. And we can see changes in climate regimes, true climate. And I'm talking, long-term climate change. And one of the things that's obvious is that as the planet heats up, the tropics expand. And all those climate belts you're taught about in school and geography move towards the equator. Towards the poles, exact opposite of that. Let me say that again. The tropics expand, and those other climate belts move towards the poles, to higher latitudes. So what we're seeing here in New South Wales will be less winter rainfall, more summer rainfall, more extreme events during summer and the shoulder periods. And one of the things that really worries me, particularly in the context of Lake George, is to see extratropical storms penetrating to here, like we saw just happen in the United States up the Appalachians, where West Virginia and North Carolina just got hammered, and they weren't expecting it. They were not prepared, and we're not prepared either for that kind of thing. But it will happen. And when it happens, it's not going to be good. And in the context of Lake George, it could bring it up 2-3 meters like that. And it can happen. And that's just one of the messages I've been trying to get across to people. And it's something we need to prepare for. Not just that sort of thing in Lake George, but just our infrastructure, just dealing with much more runoff from storms. The other thing about having more summer rain than winter rain is that the recharge is not as efficient, because when the earth bakes, it's not as hydrophilic. It doesn't take in the water as easily. So this is from Sharon's thesis, and these are sort of typical surface flow records, and what we're concentrating on, these are the groundwater levels. And what you can see where those arrows are some of the upticks in the groundwater due to the rainfall in 2010, 2016, and then in 2022. And then on the bottom there is the Murrumbidgee Bateman groundwater bore that's monitored and metered. So we actually have a record of it. And when you're talking about this sort of thing, and I think that any of you folks that actually have little pots of money that can provide helpful data to people, that kind of record is rarer than gold. It really is, because we just don't have that many groundwater monitoring stations around New South Wales, the ACT, that can show us what happened over the past 30, 40, 50 years And the Mern-Bateman one is one of the few that we have. The line through that is a model that we put together just based on rainfall deficits, where you run a running average. And this is sort of a groundwater technique where you talk about a cumulative deviation from a moving mean. And so you pick a value. And around here, typically that value is 600, 700 millimeters of rain, which is sort of the neutral value. Above that, you end up accumulating. Below that, you end up losing. And so that match is just stunning. And we were pretty pleased with that. So these are other data that Sharon pulled together. And she wants to point out that the groundwater lows before the tinderbox drought were not unique. I mean, we've had these long droughts in the past, which I showed you on that Lake George record. The groundwater system recovery sort of to 1990 levels has only just happened in the higher altitudes where the snowy hydro is. But in lower altitude catchments, that's not the case. So Burn Junk Dam, we're not recovered yet. Anamidabe, even though it's higher altitude, it's in the rain shadow, it hasn't recovered yet. But the Cotter Hut, yeah, we're almost there. So these are groundwater levels, but they're modeled. Just do that cumulative deviation. So again, I'd like you to remember that. So it takes a while for the groundwater system to recover. But a corollary to this is that it took from the mid-1990s to the tinderbox drought to totally run out of that reservoir. So it takes a long time to totally tap it out. But if you push it hard enough, you can do it. And I'm hoping for all of our sakes, we do not see another 1990, or 2019, sorry. I suppose one of the messages I'm trying to get across to folks is that what's missing is basically the Lake George portion, the cores that we saw from the lake. And in those cores, we go back in time. And we can go back 3 million years. And if we do that, we find that the lake was full. And when I say the lake was full, we're talking 37 meters deep. So you'll remember that from the last time I gave the talk. And we had Nothofagus growing around the edge of the lake. And Nothofagus requires 2 to 3 times the rainfall that we typically get in this area. So I guess the other take-home message is that those long-term climate vectors are pointing to a wetter climate as opposed to a drier one. And this is in contrast to some of the climate models that you may have heard about. And I suppose that was another main point that I wanted to raise today. So thank you for getting me back on track, is that climate models and paleoclimate data work in tandem. It's an iterative process, sort of going back and forth. The climate models will say, well, we think this is what climate was like, let's say in the Miocene when it was pretty warm. And our models say that the temperature was something like this. And we as paleoceanographers will go out into the ocean and select a site where we can test the models. We can tell them whether they're right or not. And one of the things that's really, really interesting about the Lake George record is not only is it pointing towards it being wet, and a lot of the climate models for this area, it's a coin flip, whether we are going to be wetter or drier. But almost all the data that we have point to a wetter future climate with higher CO2, which is in contrast to some of the models. So don't take the models as a given. They're always a work in progress, and they're almost always being improved. And the way we improve them is by applying data to them. And we supply that data. So those would be the main things. Thanks, Andy.
Thanks very much.